last video's site just a video of me working through these problems and kind of discussing them. It's a little long, but it's indexed, so you can just jump to whatever problem that you want to look at. It's kind of anyway. I just think it's good to practice this stuff, and then of course on test 2 and the final exam, there's going to be stuff on chapter 5. Just in general, I think what I'll do is just sort of pass around this clipboard for if anybody wants to write down for volunteers. It's two-sided there. Just sort of the front rows. I was thinking. Yeah, this is a good one. It's from Anonymous from last week. It starts with, hi, I have a dumb question, and then the student goes on to ask an extremely good question about whether the normal force on one of these carts is equal and opposite to the gravity force. And so I really do believe that there are no dumb questions. I think if you're sitting there thinking it and wondering it, and kind of, afraid to raise your hand and actually, ask about it, the odds are that 80% of the students in the room are thinking the exact same thing and also afraid to ask about it. This is true in all of your classes, by the way. And so it takes some courage to actually shout out and interrupt me and take some time to actually deal with what you're wondering about. And that is the reason I am here, right? I suppose you could go and watch a brilliant video of an MIT professor teaching this stuff and learn even more than you would from just listening to me teach this stuff. But, you'd never be able to ask questions. There'd be no back and forth. And so let's not fall into that trap where I just talk, you just sit there. I'm throwing these learning catalytics questions at you for a reason, because I want you to be active. And you should throw your questions at me so that I'm actually helping you. That's what I want. So one way of doing that is if I should have a better eye on the classes of ed discussion, but I just don't because there's too many computers up here. So if you want to sign your name on the clipboard on one of these days, then I'll assign you to be the person who yells at me when there's something interesting going on. Okay. So last time we were talking about conservation of momentum, this sort of new concept where there's a collision, some sort of quick interaction between two objects in which you look at the momentum just before the collision and just after the collision. So for example, if you hit a ball with a baseball, what's important there is for the baseball's motion or something is that exterior force of the bat on the ball. And so all the internal forces which hold the baseball together don't contribute to a change in its momentum. And similarly, if you're stuck in a car and you want to get it going, you can't push on the dashboard of the car and get the car to move. And that is because you are internal to the car. And you need an external force to get that car's momentum to change. And in this case, the external force, we talked about this, I think it's actually the friction, static friction of the ground on the car is that external force. So in the DSM I asked you to do, the dynamic study module for this stuff, there was all this stuff about the impulse approximation, which isn't really talked about too much in the textbook, but the idea with it, hopefully you were able to kind of trial and error your way through it, is that for most collisions, the forces involved in the collision itself are much greater than like the external forces of friction of the ground on something. So when this police car hit this streetcar, there was a huge force between the streetcar and the police car, and for a very, very short duration of time. And during that time, the impulse approximation is that you neglect actually friction from the road on the police car or the streetcar. So what you do is you sum up all the momentums of all the objects before, and you set that equal to the sum of all the momenta of all the objects after. So that's sort of what this conservation of momentum equation looks like. And so that's one example. The other example where the impulse approximation comes up a lot is in explosions. You take something blows up like a firecracker. If you take the momenta of all the pieces and add them up, it should be equal to the momentum of the firecracker just before. And that is because during the explosion, the forces on all those fragments is much greater than the force of gravity, for example. And it's such a short duration that you can neglect any impulse from gravity. Again, impulse approximation. Okay, so what we're going to do next is deliver this first one on your, hopefully you see it on your device. Idea is that a basketball is traveling just before it hits the floor at a 45-degree angle, going down and to the right. So 5 meters per second to the right, 5 meters per second down. It hits the floor and then it bounces up. And when it bounces up, it keeps the same x component of its velocity, but it reverses the y component, but not quite fully. Like I think it ends up with plus 4 meters per second in y. Anyway, the question, they're going to ask you two questions. One is what's the impulse, x impulse, and then, which is, impulse, by the way, is the same as change in momentum. And then second question will be what's the y impulse. So if you get this one, you can check the next one. I'll give you maybe a minute for each of them. Maybe think about it, and then check with your neighbor, if you have a neighbor. Go. Okay, so let's do, people think about what is the change in the x component of the ball's momentum during the collision? Going once, going twice, and survey says I got 308. People, 85% of you are saying 0, so that's the idea, is that it's actually, what's interesting too is that the force is the normal force during that collision, and so the normal force is in the y direction, so it sort of makes sense that it's not going to change the x component of the velocity because there's no impulse. But basically one way of looking at it, if we go to blue here, is that P initial in the x direction is equal to the mass times plus 5, and P final in the x direction is the mass times plus 5. And so delta P is equal to delta Px is P final x minus P initial x, and you get 0.5 minus 0.5 equals 0. And next question is this one. Same question with the y component. Okay. Hopefully your neighbor agrees with you. If you could click in 15 seconds and we'll move on. Okay. And survey says, there's a 309 here. A lot of people are saying plus 0.9 kilograms meters per second. So almost all of you. So what I think is, let's see here. P initial in the y direction is 0.1 times negative 5 meters per second. So that's equal to negative 0.5 kilograms meters per second. And P initial in the y direction is, P final, that's P initial. P final is 0.1 times plus 4 after it bounces. So it's equal to plus 0.4 kilograms meters per second. And so delta P is equal to, it's always final minus initial. These are all components. So the final being plus 0.4, and then the minus the initial. Oops. Minus 0.5. When you subtract a negative, you get a positive, so it's plus. It's 0.9, plus 0.9 kilograms meters per second. And that is coming from the normal force. Again, it's an upward force over some small duration of time, gives you a change in momentum which is upwards. So this is called impulse, which you've read about, but basically the impulse on a particle is the average force times the delta t. So if this is the average force right there, and this area here is a rectangle, then this would be t final, and this would be t initial. And then the area of the rectangle is the base, which is t final minus t initial times the height, which is F av, okay, the average force. And there's two equations for impulse because impulse is a vector and momentum is a vector. One is the x impulse and one is the y impulse. I'm not sure why it's J, but J is the letter they use for impulse. I think I must be used for something else. Impulse has units of newtons times seconds, as you can see there, but you can also show that that's equivalent to kilograms meters per second. And the impulse momentum theorem just says that the change in a particle's momentum is equal to the impulse on it, external impulse. So let's try another question, which I'll deliver to you guys. It looks like this. You are shown the graphs of the x and y components of the force on a hockey puck. So maybe you're looking down from above or something that's sliding on this frictionless surface. So you can imagine that it's maybe x is the east-west axis and y is the north-south axis, for example. And the graphs show the x component of the force versus time and the y component of the force versus time. And you see these spikes, and that's very typical for impulses. There's a very large force, but delivered over a very short amount of time. It gets hit, maybe hit with a hammer or something, or hit with a hockey stick. And then the question is, if that happens to it first at 1 second, then 2 seconds, and you kind of label the path of the puck, which of these paths is a possible path for the hockey puck? How are people doing with this? Try to make sure you're in agreement with your neighbor. Yeah, correct. Yeah, so first there's a positive x impulse at time t equals 1 second. Then there's a positive y impulse at t equals 2 seconds. And what does an impulse do? And what does an impulse do? Does anybody know? Changes the momentum, exactly. So a y impulse changes the y component of the momentum, and the x impulse changes the x component of the momentum. Okay, you guys want to click in and to discuss this? This takes a little bit of practice. I can tell you this isn't going very well, so let's discuss it. Going once, going twice, and so most popular answer is the path C, which I didn't like. So the way I'm thinking of it here is that you're looking for something. So if it's moving from time, so this is a situation where the initial velocity is to the left. Okay, good. So then somehow it has to receive an impulse to get it to go straight up. Well, that would be an impulse. I don't know how 1 and 2 would be all together, but 1 and 2, so it would, I guess, stop after 1 second, so there'd have to be a big x impulse. So actually that could be correct, actually. And then, wait, why can't it be this? Then it could just go straight up. I'm wondering if A could be correct. Okay, let's see about the next one. The next one is that it starts with some initial velocity down. It then receives an impulse to the right, which would turn it. So it continues with its negative y velocity, but then it gets this x component. And then it gets hit with a positive y, and so that's going to continue with its y component, but then maybe stop it. So then it'll turn this way. So this also looks okay. So far I like A and B. Now I'm trying to think if anyone knows any reason of why A is not correct. Let's look at C. So C is that it's initially stopped, and then you give it some x component, so it goes along like this. And then from 2 to 3, it goes straight up. So this requires both a negative x component and a positive y component. So this impulse would have to be like that. So negative x and plus y. So it can't be C for sure. For this one, it starts with a down, and so negative x and negative y momentum. It then changes by, basically it has to have an impulse to the left. So that's okay. And then when it gets here, it stops. So again, D is okay. The only one I don't like is C, actually. That's the only one I cannot possibly be. which was the most popular answer. So, so I'm going to change that around and try to accept A. So A, B, or D both all make sense to me, I think. Unless I'm doing something wrong there. But definitely not C. Any questions or comments on that? Anybody brave enough to write their name as a volunteer on the clipboard? So far we've got one volunteer, which is kind of funny. You are? I don't know. Yes, question. So the answer is either A or B or D are all fine, depending on the initial velocity. But so there's some initial velocity, and the question is, what could it be? So, and what's going to happen is at 1 second, you need to deliver an impulse which changes in the positive x direction the velocity. And so in the case of B, it just turns it in the positive x direction. And then you deliver another impulse at 2 seconds, which changes its velocity in the plus y direction. So it turns it again at 2. So B is clearly correct. What happens with A and D is that there's a stopping. So it starts by going towards the left. That first x impulse stops it, which is okay. It sits there for a second. And then at 2, it gives it a kick in the plus y direction. It goes up to 3. So A is okay. And then for D, it's initially got negative x and negative y components. So the first kick in that positive x direction, I guess, takes that x component down to 0. So it's just going straight down. And then the second kick stops it and just sits there for 2 and 3. I should have checked this question a little better, sorry. Okay, but it's good to sometimes discuss these things, right? And I can always fix the marks after. Yeah, which one is not a correct answer that you'd all get? Or anyone who answered C would have been right. That's not what I asked. Okay, let's do another example. A 0.51 kilogram baseball flies to the left with an initial velocity of negative 30 meters per second. And then Vladimir Guerrero Jr. hits it and provides an average force during the hit of 12,000 newtons to the right. But the duration of the hit is only 1 millisecond. Okay, what is the impulse delivered to the ball and what is the velocity of the ball immediately after the hit? So, I would say that the impulse, J, in the x direction or something, is the force times delta t. So it's going to be 12,000 newtons times 10 to the minus 3 seconds. So I got, you can just bump this decimal 1, 2, 3, you get 12. So it's plus 12 newtons seconds, which is the same as plus 12 kilograms meters per second in SI units. So that's good. And then you've got P initial of the ball in the x direction is maybe the initial x. So that's 0.15 is the mass times negative 30 meters per second. You get P initial x is equal to negative 4.5 kilograms meters per second. And then finally, P final in the x direction is P initial x plus the impulse. So that's how you do this. So you get negative 4.5 plus 12 is plus 7.5 kilograms meters per second. So he hits it. And now it's going in the opposite direction. And so then you can do, finally, V final x is equal to you've got the momentum, so just divide it by the mass, and you get 7.5 divided by 0.15, so you get plus 50 meters per second. So he gets a home run, because that's pretty good. So it's a lot simpler than working out the force diagram and the acceleration and the time and all that stuff. You can just use impulse. Okay. So that's the power of this whole method, is that if you have a large force over a very short amount of time, you can find changes in momenta and then figure out what's going on. All right. So here's some other examples of how the impulse momentum theorem, so impulse momentum theorem, what it says is that the force you exert multiplied times the time that you exert the force gives the change in momentum on the object. So here's some examples. Following through, so people say when you swing in baseball or when you swing in golf or something, you should sort of follow through. You should continue kind of moving as you're hitting it. And what this does is this applies the greatest force, first of all, by swinging it fast, swinging the club fast, and second of all, by extending the amount of time during the collision. So So I think that somehow following through does both of those things. Rather than trying to check your swing, that might decrease the amount of time. You want to increase the time of the collision and increase the force to get it going fast. So this is a falling with style. Bungee jumping. If you jump off a bridge and you start to approach the river below, then at some point, if you don't want to hit the river, you're going to have to decrease your speed. So you're going to have to reduce your momentum from whatever it was, from falling, down to 0, because you can't obviously go into the earth, right? So there's 2 ways of doing that. You can do that with a very short amount of time and a very high force, because your impulse could be changed from whatever your speed was to 0 in 1 of 2 ways. You could hit the rocks, or you could, the bungee could apply a force to you. So the rocks, it would be a very short duration impact, so you need a large force to give you a certain impulse. Whereas the bungee has a long duration of force, so delta t is very large, so you can reduce your impulse or reduce your momentum with the same amount with a smaller force. So what you want to do is increase the time of the force in order to decrease the magnitude of the force so that it doesn't hurt as much. Extend the time during which the momentum is reduced. This could be also, here's some actual, trying to draw it out. F times t is the change in m times v, right? M times v is the momentum, which is changing some amount, and F times t is the impulse. So if you are in a truck with some m, some mass, and a large velocity, then it's going to get reduced down to stopping, either by a small force and large t, like you're plowing through a bunch of hay, or if you hit a wall, that would be a very small t, but a very large force. Both of which achieving the same thing, which is that all your momentum goes to 0. Crashing with style. There's getting... So I go a little far with this joke, but they say, if you're going to get punched, try not to really stand perfectly still. You kind of got to let yourself get punched, meaning that you extend the time over which that fist is hitting your face, and therefore the force on your face can be a little less, even though your head changes momentum by the same amount. So, and then you can do exactly the opposite. If you want to karate chop through a stack of bricks, you can try to reduce the amount of time of that impact and for the same change in velocity and greatly increase the force. Time of contact is brief, the force of the impact is huge, and you can chop right through the bricks. Okay, should we do demo? Here's a demonstration about impulse and see how this goes. 2 balls, and I'll start, I want you guys to predict, so I'll put it on your learning catalytics as well. I have 2 balls of the same mass and same speed. They collide with a block of wood, sort of as shown there. One ball is made of rubber and bounces backward when it hits the block of wood, and one ball is made of putty and stops when it hits the block of wood. I'm going to do the rubber ball first, I think. Which ball delivers the larger impulse to the block of wood? So A should be the same. They're about the same mass. And they're going to have the same speed, actually. And then B is you're voting for putty, and C is you're voting for rubber. So that should be on your learning catalytics. And we've got it actually, Pius set it up so that here's a rubber ball. It's in a clamp. Here's a clay ball, which is kind of squishy. You like it a little bit warmed up, so it's nice, so it doesn't bounce. A little bit spherical. Oh, spherical. I see. Okay, good. So try to make a prediction. I think they're going to end up doing different things. But this one doesn't bounce because it's made of clay. Get rid of this. We don't need the basketball. Did you make a prediction? Should we actually see what the prediction is? Oh, dear. I hate that green thing. It's the worst. If there's something I could change about learning catalytics, they would all be the same color. Okay, so let's pretend we didn't see what was which. Let's see what happens with the rubber ball first. I think I just unscrew this. Top one maybe. Let it fall. Ooh, okay, so that knocked over the block. Now we'll set the block up exactly where it was. Remove this hook on the clay ball. Put that in the exact same starting position. Grab on, ready? It doesn't knock it over. So what I would argue is that the bouncy ball reversed its momentum when it hit. And that requires twice the impulse from the block as does the clay ball. The clay ball, when it hits, just stops. The rubber ball, when it hits, bounces. So I guess whatever its initial velocity was, it has to reverse it. That has to stop it and send it off in the other direction. Whereas with clay, it just has to only stop it. Make sense? That's what I was going for there. You guys have miraculously predicted that correctly, so that's good. So, point being, so it's rubber. Whoop, thank you. See rubber. What I would say is that both balls have equal initial magnitude. Initial momentum, because they're the same mass and they were released from the same height. The difference here is that the putty ball, or clay, stops. So delta P, I guess, whatever its magnitude is approximately equal to the P initial. Whereas the rubber ball bounces. So backwards. And so the delta P is approximately equal to P final minus P initial. So it's going to be about equal to 2 times P initial. Something like that. Twice as much. And so that's the impulse that the block exerts on the ball. And then by Newton's third law, that's also going to be equal to the impulse that the ball exerts on the block. Does that make sense? Okay. So that's the bouncing. Impulses are generally greater when objects bounce. For example, if you catch a falling flower pot from a shelf with your hands, you provide the impulse which reduces the momentum, the downward momentum of the flower pot to stop it. But if you throw it back up again, you're going to have to give it even more force and more impulse, twice the impulse to make it go up again. That's a double impulse. So that's bouncing. And you can see the way these buckets are shaped in this, it's called a Pelton wheel. When you've got a waterfall coming down, you're trying to generate a force. These buckets are designed to actually splash the water back up, which then again can about double the impulse on the wheel from the water. So You can graph these, and the book does this a bit, and it's kind of hard sometimes to keep track of what's on what. So if the system is the ball, and then the external force is coming from the wall, and the x is in this positive direction here, sorry, to the right, plus x is to the right, then what initially is happening when a ball hits a wall that's traveling to the right is it has some x momentum. Then during contact, there's a huge change in momentum. It maybe ends up with negative, right, of that initial momentum. And what we're saying with the impulse momentum theorem is that this negative force in the negative direction of the wall on the ball, if you take the area under that curve, you get the change in momentum, delta P. Okay. And let's look a little more carefully at how your book exactly defines that. So the way Yatkina goes through this is, she says, initial plus the delta equals the final. I actually kind of like that. I think it's a little easier, especially with vectors, is that the initial momentum, which is a vector, plus the impulse, which is also a vector, it's the letter J, is equal to the final. Because I find it easier to add vectors than I do to subtract. The delta is always final minus initial, but another way of putting it is whatever your initial is, add the delta, you get the final. And then she splits it up into x and y components that looks like this. So this is, by the way, the sum of all the initial momenta, plus the impulse, external impulse, is the sum of all the final momenta. So the impulse is the force times the delta t. There's your initial momentum, and there's your final momentum. So it looks a little messy. But the basic idea is if the impulse, the net impulse is 0, that's when you have conservation of momentum. There's no external net force exerted over some time. Then the P initial on the left plus 0 equals the P final on the right. And there's this recommendation in the book, and they do all their examples by using these what are called bar charts. And this is going to come up again in chapter 7 a lot when there's energy bar charts. But the way they look is this. You've got positive quantities represented as these upward bars on a bar chart, and negative quantities being downward, and zeros in the middle. And what they do is they can cancel each other out. An upward bar plus a downward bar of the same height, you add them up and you get 0 in the middle. So if you have two carts that are moving towards each other, and one has a large momentum in the positive direction, and one has a small momentum in the negative direction, if you add them up, and there's no external forces, so Fx equals 0, then in the end, if they're stuck together, they have to share what remains. So this is 1, 2, 3 minus 1. 3 minus 1 equals 2 to share. And so 1 plus 1 in the end is the momentum they've got. So it's just a sort of a graphical way of conserving a quantity, such as momentum or energy. So the way you do it, if you look at the sort of the 4-step method, first you sketch the process and label what the initial and final states are. Second is you can, during that sort of simplifying diagram, you can draw momentum bar charts if you want, if that helps you kind of sort out your thoughts. But that's getting you to an equation, which is P initial plus the impulse equals P final. And then, yeah, that's sort of the represent mathematically stage, and then you solve it out, solve and evaluate. So the lengths of the bars are qualitative indicators of the relative magnitudes of the momenta. The middle shaded column in the bar chart represents the external, so that's the one after the initial. And then the sum of the heights of the bars to the left of the equal sign equals the sum of the heights to the right of the equal sign. So the conservation of bar heights reflects the conservation of momentum. So just to give you a quick example, let's do a typical question. This one is problem 6.68 from your textbook. Where the heck is it? Let's see here. Which is, you got a 0.02 kilogram bullet traveling at a speed of plus 300 meters per second, embeds in a 1 kilogram wooden block that's resting on a horizontal surface. Then the block slides horizontally 4 meters on a surface before stopping. Determine the coefficient of kinetic friction between the block and the surface. So this is going to be one of those two segment problems. There's two things happening. First, there's a collision. So you've got before and after the collision. And then there's another segment of motion, which is the sliding, for which we'll use, I guess, sort of chapter 4 material. And I think somebody asked me, is test 2 cumulative? And my answer was, not really. I'm just going to be picking questions from chapters 5, 6, and 7, but the nature of physics is that it is kind of a cumulative subject. So let's call B is the bullet, and I need another, instead of block, let's call it the wooden block, W, just to keep our things together. So then let's do this into 3 stages. One is before the collision, and 2 is going to be just after the collision, but before it slides. And then 3 is going to be the sliding motion. So that's how I'm going to try to separate my thoughts here. So before the collision, I've got a little bullet, which is traveling along. Here's mass of the bullet. And the V bullet 1 is the 300 meters per second. And you've got a block of wood sitting over here, the mass of the wood and the velocity of the wooden block, 1 equals 0. And it's sitting on some surface. Okay? And then just after the collision, you've got, it kind of looks like this. The bullet is, it says embedded, but it means it's stuck. It's stuck in the wood. So it no longer has any relative motion inside the wooden block. So they now kind of move together. So I'm going to define MBW is the mass of the bullet plus the mass of the wooden block. And the question here is VB2 is question mark. I'm going to try to find, which I think I have enough information, using impulse momentum to find VB2. And then what I'm going to do is this sliding motion is that the initial is VBW2. So there's this block with a bullet inside it, and it goes along some distance. X is 4 meters, and then it stops. The final, I guess VBW3, I guess, equals 0. And I know here that as it's traveling, there's some sort of force diagram where F sub k is, I guess A is equal to negative F sub k over m, something like that, in the x direction. And F sub k is mu sub k times the normal force, and the normal force plus or minus mg equals 0. Something like that. There's going to be a bunch of stuff that we've done from before. So that's supposed to be minus sign. Okay. How are we doing for time, guys? Yeah, we've got 5 minutes. We can solve this. So in the simplify and diagram stage, first I'm going to start with this collision and look at these momentum bar charts. So what we've got is the bullet has some initial momentum. This is bullet. And then the wooden block has none. Plus, there's no external impulse, J. And this is equal to this same amount of momentum in the bullet and the wood together. So the way this looks in terms of equations is the mass of the bullet times the speed of the bullet, 1, plus 0, is equal to the mass of the bullet and the wood together times VBW2. Thank you, guys. So that means that VBW2 is equal to the mass of the bullet divided by the mass of the bullet and the wood together times VB1. So we know all those numbers. So we can just say that VBW2 is equal to 0.020 divided by 1.020. That's when they're together, times 300. So that equals 5.882 meters per second. Okay, so what's known here for the sliding motion is VBW2 and VBW3 equals 0 and x, and we need a sub x. So we're going to use VBW3 squared is VBW2 squared plus 2 times a sub x times x. So that's just a kinematics equation where the final is that 3 after the sliding motion, and the initial is just after the collision, but before it starts sliding. And so AX is going to be negative VBW2 squared divided by 2x. So I can just figure that out. Negative 5.882 squared divided by 2 times 4 meters. So I know that the acceleration is negative 4.325 meters per second squared. And I also know that A sub x, this is Newton's second law, is the force, is negative the kinetic friction force divided by m. So that's going to be negative mg times mu sub k divided by m. The m's cancel. And I'm going through all this chapter 4 stuff a little fast because you're probably familiar with it. So I'm going to now solve for mu sub k. Mu sub k is equal to negative ax divided by g. So it's negative of negative 4.325 divided by 9.8. So I got mu sub k is equal to 0.44. And the units cancel, which is good. It's also good that this is between 0 and 1. As all these coefficients of friction seem to be. Okay. So I'm going to try to find the clipboard. You can raise your hand if you're holding on to it. Does anybody have the clipboard? There it is, great. Yeah, so before Friday, please finish up with chapter 6, because Monday we're going to start in on chapter 7, so also bring your questions. We'll try to, hopefully we'll get someone to volunteer to look at that. Yep.